Hello everyone, my name is Quanshi Zhang. I'm an associate professor at the Shanghai Jiao Tong University. This tutorial is on the theoretically unifying conceptual explanation and the generalization of the DNN. In this tutorial, I will introduce game theoretic interactions as a unique theory to unify the attribution explanation, the encoding of visual concepts, the generalization power of the DNN, and the adversarial transferability and robustness. The first question is that why the interpretability of a neural network is so important. Actually, if we only focus on some simple tasks, for example, the image classification, whether or not a model is interpretable is not so important. But if we focus on some crucial tasks, such as the finance, autonomous driving, medical diagnosis, and military tasks, the interpretability of a model is very crucial in this case. So this figure shows the growth of the paper in the explainable AI. In recent years, people gradually consider the interpretability of the model is a crucial component for the artificial intelligence. At present, there is no unified framework for explainable AI. We can roughly divide all topics into two directions. First direction is a semantic explanation of a neural network. The second direction is the mathematical explanation of the representation power of a neural network. In the first direction, people usually consider which semantic concepts are learned by the neural network and which semantic concepts are used by the neural network for prediction. How to quantify and improve the trustworthiness of a neural network. How to learn the interpretable features for the neural network in an end-to-end manner. How to directly communicate with the concept encoded in the intermediate layer of the neural network. In this way, to learn new concept. How to evaluate the explanation result. In the second direction, people usually focus on these problems. For example, how to model and explain the representation capacity of a neural network. How to bridge the architecture of a neural network with the knowledge representation. And how to bridge the knowledge representation with the performance. It's because the architecture of a neural network doesn't directly determine the performance. The architecture determines the knowledge representation encoded by the neural network, and the correctness of the knowledge determines the performance of the model. Third, how to explain the classical deep learning techniques, for example, the knowledge distillation, the adversarial learning, and the network compression. And finally, one of the final goals is how to debug the neural network. That's all topics, but we do not have a unified framework for all of these topics. This slide provides some example of the semantic explanation of a neural network. For example, when a model makes a decision that this patient needs a surgery with a confidence score 0.9, the explanation method may estimate the exact reason why the model makes such a prediction. Maybe the first region provides the confidence score of the 0.2, the second region provides the confidence score 0.1. We need to quantitatively evaluate the importance of each region, the exact reason why the neural network makes such a prediction. And another issue is that maybe the estimated reason is not the true reason of the prediction, and the true reason of the neural network may not be so reliable. For example, when the neural network classify whether this girl wear lipstick or not, we do some experiment. We paste another lipstick, another lip to this girl, or we mask the region of the girl, the mouth region of the girl. We found that the score of lipstick do not change greatly, significantly. So we can visualize the attention of the neural network. We can see that the neural network made the prediction based on the eye features, the nose features, the cheek features, not only the mouth features. And here, this is another example. This is a accurate. This is a correct prediction. So the neural network classifies this image as a horse, but the reason is not the appearance of the horse, but the words here on the bottom left. The model used the words on the bottom left for classification. So some people visualize the receptive field of the filter in the intermediate layers to explain the attention of the neural network. This is a typical work for semantic explanation of the concepts encoded in a neural network. Then the second direction is the mathematical explanation of the representation power of a neural network. Let us take the autonomous driving car, for example. This autonomous driving car has a safety run for a year. Then what's the true accident frequency of this car? Is it once per year or once per 10 years? If we do not have any accident records, it's very difficult for us to estimate the true accident frequency. And more crucially, how to further boost the safety of this car without any accident records, without any negative samples to fine-tune the model. This is a very crucial problem. How to further boost the performance neural network even without any negative sample. All of this problem should be solved in theory. We need a new theory to formulate this problem. So we need to we face these questions. How to evaluate the generalization power of the neural network? Why does a specific DNN architecture outperform other architecture in a specific task? What's the relationship between the architecture and the knowledge? What's the common essence of existing deep learning methods, and how to further improve this method? First, let us discuss the problem with the semantic explanation of neural network. There are 4 problems. First, different explanation method usually only can satisfy the self-consistency, but they cannot satisfy the mutuality between different methods. Let me take the attribution method for example. This is an input image. Then all the attribution methods provide the attribution map of different input pixels. That's this method estimates the importance of different input pixels. And the different methods are designed based on different assumptions. Each method is reasonable, but they generate different results. Their explanation results conflict with each other. So this method can only satisfy the self-consistency. There's no mutuality between these attribution methods. Second, there are very few theoretical foundations for the explainable AI. As a result, because we have no theoretical foundation or we have very few theoretical foundation, it's very difficult for us to improve the performance of a neural network. It's a very crucial problem. because one of the final goals of the IJCAI is to improve the performance of the neural network. Finally, there are a lack of the convincing evaluation metric to evaluate the quality of the explanation. That's the four problems with the semantic explanation of the neural networks. That's the problem with the semantic explanation of neural network. Then let's discuss the problem with the mathematical explanation of the representation power of the neural network. Most of the studies for explaining of the representation power of the neural network are usually designed based on certain assumptions, but these assumptions are not so realistic. For example, they assume that the neural network are very shallow, or they have infinite width. And the second issue is that the mathematical bound for the neural network is not equivalent to understanding the true reason for the representation power, because the mathematical equation is not equivalent to the intuitive understanding of the true reason of the performance. And another issue is that an important issue for the deep neural network is that there is an emergence of the semantics in the intermediate layers, but the current studies cannot explain the emergence of the semantics in deep layers. In this way, we can roughly consider the current research of IJCAI is a technology rather than a science. So we need to focus on three terms in order to push the current study from the technology to science. The first is the regional explanation of neural network, the semantic explanation of the neural network. We need to ensure the strictness of the meaning of the explanation. Because if we use visual concept to explain the neural network, we need to ensure that the neural network have really encoded such visual concept, and how to clearly quantify the boundary of each concept, how to accurately estimate the attribution of different concepts. But this is a great challenge for current studies, because there are no theoretical formulation for different concepts. What's the true definition of different visual concepts? Second is that we need to propose more IJCAI metrics to measure the representation power of a neural network. Third, we need to provide more theoretical foundation for the current studies. So we need to focus on these two terms. First is the neutrality between different metrics. Different people study the neural network from different perspectives. Some people focus on the transferability of the features. Some people focus on the adversarial robustness and the transferability. Some people focus on the transformation complexity and the generalization power, the disentanglement of the feature, the information of the feature, and the interactions encoded inside the neural network. But all of this metric can just provide a single view to diagnose the neural network, but the different research are developed using different assumptions. They are not formulated in a single system, in a single theoretical system. So there is no bridge, no theoretical connections between these terms. So in this way, we need to build up some theoretical connection between the transferability, the robustness, the complexity, the generalization, disentanglement, and the information in a single theoretical system to ensure the mutuality between different metrics, to boost the trustworthiness of the current study. Second is that Most deep learning methods in recent years are developed in heuristic manner. These methods are developed based on the experience of the researchers, and the different methods all have good performance. But we need to summarize the common essence of this method. Which factor makes this method effective? We need to summarize the common effective factors for all the heuristic methods. In this way, we can improve based on the common essential factors. We can improve the current studies. And finally, the final goal of IJCAI is to use the explanation result to guide the architecture design of the neural network and to guide the learning process of the neural network. To this end, in order to unify the various explanations of the neural network, in recent years we developed the game-theoretic interaction. That's to define the interaction of the input units in game theory. The theoretic foundation is the game theory, or typically the Shapley value. Based on the game theory, we define the interactions of the input units of a neural network. Specifically, we define the multivariate interactions, define the multi-order interactions, and we derive some properties of these interactions, and we propose how to learn. Based on these directions, we propose how to learn the baseline value for Shapley values. And then that's the achievement inside the game-theoretic interactions. Based on the such interactions, we can explain the representation power and the semantical concepts encoded inside neural network. For example, we can use the game-theoretic interactions to explain the generalization power of the neural network, to construct an interaction tree, to explain the semantic hierarchy of the neural network, and to explain how the neural network encodes different concepts, different visual concepts inside neural network, how a neural network encodes textures, and how a neural network encodes shapes, and explain the adversarial transferability of the neural network, explain the adversarial robustness of a neural network, and explain the semantic level of an input image. So we can use this single theoretical system to explain the neural network from different perspectives. First, I will introduce the theoretical foundation of game-theoretic interaction. That's the Shapley value. For Shapley value, we can consider the input variables of a DNN as the different players. We can consider the scalar output of the neural network or the loss value of the neural network as the total reward of all players in the game. So in the game, different players cooperate with each other to win a high reward. So in the DNN, different input variables cooperate with each other to make the prediction and generate the network output. In this way, given a neural network how to fairly allocate the reward to each player is the key problem to explain the neural network. So the Shapley is considered as a fair method to fairly allocate the reward to players. That means the Shapley value, if we consider the game as a neural network, the neural network as a game, then we can assign the attribution to each input unit, that's to each player. So we can consider the Shapley value measures the reward assigned to each player. That means the Shapley value measures the numerical contribution of each input pixels to the prediction result of the neural network. So here is the result, the numerical contribution of each pixel estimated using the Shapley value. So phi I given n is the Shapley value of the ith input pixel, and Vn, that's the output of the neural network given all the n pixels. N is a set of the pixel of all n pixels, and so we can use this equation to compute the importance of each input unit for the prediction of the neural network. The Shapley value is widely considered as the unique standard attribution metric that satisfies the following four properties, which ensure the fineness of the Shapley value. The four properties include the linearity property, the dummy property, the symmetry property, and the efficiency property. Let's first focus on the linear property. If the two independent games can be merged into one game, then the Shapley value of the player I in game V and in game W can be merged. That means if the same image are given into two neural networks, one neural network is V and another neural network is W, and the final output is the sum of the output of the neural network, then the importance, a single pixel's importance to the first neural network, and plus this pixel's importance to the second neural network equals to the importance of this pixel to the overall output of the two neural networks. Second is the dummy property. A dummy player satisfies that a player I has no interaction with other players. It means that if a pixel in an input image has no interaction with all the other pixels, then the Shapley value or the importance of this pixel equals to the marginal effects of this pixel. And the third property is the symmetry property. If the two players and the two pixels have the same collaborations with other pixels, then they have the same importance. That means in an input image, if two pixels have exactly the same collaboration, same interactions with other pixels, then the importance of these two pixels are the same. Finally, the efficiency property. If we sum up the reward of all players, we will get the overall reward. It means that the overall utility of the network output can be finally assigned to all input units. However, there are two remaining issues for the theoretical system of Shapley value. First is how to determine the reasonable based on values. Second, how to determine the reasonable partition of players. For example, for image processing, people usually consider a single pixel as a player. But is there any more reasonable partition of the players? Maybe we need to combine two pixels as a collision and consider a single collision as a player instead of using each pixel as a player. So the second problem is how to determine the reasonable partition of players. So in the first section, I will introduce how to define interactions in game theory. What's the game theoretic interactions? The interaction means the collaboration between input units of a neural network. For natural language processing, the input units are input words in a sentence. And for image classification, the input units are pixels in an input unit in an input image. So the DNN usually doesn't use a single word for prediction, but use the collaborations of different words to form a phrase and use the phrase patterns for prediction. For image classification, the neural network doesn't use a single pixel for prediction, but use different pixels to form a certain shapes. Use the shape features for classification. So in short, we consider the interaction between different units as follows. Let A and B and C, the three guys, let us consider the three guys as three words in an input sentence. We just evaluate importance of these three words, of the collision of these three words, and then we evaluate the importance of the Shapley value of each word. If the word Alice, word Bob, and word Carlo just work individually, we can evaluate the importance of this word. So if the sum of the three words is significantly larger than if the attribution or the importance of the three words is significantly larger than the sum of the importance of each word, that means BA, this is greater than 0, much greater than 0, then the three words can be considered to have a cooperative relationship. They help each other to make a more significant influence on the input, on the prediction result. And if the importance of the collision is smaller than the sum of the individual importance, then the interaction is negative. That means the three words fight against each other to decrease the influence between them. So they have, in the first case, they have a positive interaction. In the second case, they have the negative interaction. If BA equal to 0, that means there is no interaction between the three words. In this way, the interaction between two words in a sentence is quantified as follows. Let's consider the interaction between two words I and J. The interaction I and J is quantified as this importance minus the second importance. The first importance means the Shapley value of I when the word J is always present. The second is the Shapley value of word I when the word J is absent, is always absent. So this value measures, when we use this importance to minus this importance, this value Iij measures the influence of word J on the importance of word I. That means whether the presence or absence of word J can affect the importance of word I. Whether the presence of word J can change the importance of word I. If they can, then word I and J have considerable interactions. So we consider and we derive some properties of the multivariate Shapley values, the multivariate Shapley interactions. They satisfy the linearity property, the dummy property, and the symmetry property. Note that the different partition of the words may lead to different interactions. Some words may have positive interactions, they cooperate with each other, but other words may have negative interactions, they fight against each other. So the partition of the word determines the interactions between words. So in this way, I just design a method to quantify the overall significance of interactions encoded within a phrase of the words, within a phrase. So I compute the partition of the words that maximize the overall interactions between the phrases. And I compute another partition of the words that minimize the interactions among words within the phrase. So I just compute the maximum interactions minus the minimum interactions to quantify the overall significance of the interactions encoded within a phrase. So this method can effectively measure the overall strength of interaction encoded in a certain phrase within a sentence. In this way, the multivariate interactions can be used to extract the tree structure that reflect the implicit hierarchical relationship between words of the input data. So in each step, I merge two words or merge the labeling phrase that maximize the interactions. So in this way, we can obtain the hierarchical structure of the input sentence. All the methods can be also used to extract the prototype feature to understand the incorrect prediction of a neural network. So, given a sentence, let us take the sentiment classification for example. And for given this input sentence, the prediction is negative, but the ground truth is positive. So we can mine the phrase that contribute to the current prediction, the negative prediction. And we can also mine the phrase that whose collaboration contribute to the positive prediction. So the inference process is a trade-off between all the reasons for negative prediction and the reasons for positive prediction. So the collaboration within these four words contribute to the accurate prediction of the positive label, and the collaboration between these two words contribute to the incorrect prediction of the negative label. Furthermore, we can also define the multi-order interaction to represent the complexity of the knowledge representation encoded in a neural network. Just in the previous slide, I defined the multivariate interactions, the interaction between different units. Then in this slide, I define the multi-order interactions. The order of interaction represents the complexity of the interaction. Let us consider the interaction between two units I and j. But actually, the interaction between I and j does not exclusively depend on the two units I and j. Many contextual input units are involved in the interaction. So the order m of the interaction between interaction I and j is quantified the number of contextual pixels that are involved in the interaction. That's RMIJ measures the average interaction between pixel ij and all contexts consist of m pixels. So the low-order interactions usually represent simple contextual collaborations with a few pixels. So the low-order interaction usually represents simple concepts. But the high-order interactions indicate the complex contextual collaborations with massive pixels. So the high-order interaction usually represent the complex concepts. For the multi-order interactions, we also derive a total of 7 properties for multi-order interactions, including the marginal contribution property, the accumulation property, efficiency, linearity, independency, symmetry, and soundability properties. So the second issue is how to determine baseline value for Shapley values. That means how to use the game strategy interaction, the theory of game strategy interaction to help refine the theory of sharply value. To its end, we use this theory to model, to formulate the learning of baseline values for sharply value. Then what's the problem with the baseline value? Let's first revisit what is the sharply value. Let me consider the sharply value of this image region inside the input image. The sharply value is computed as the weighted sum of the marginal effects of this image region. VSI minus VS. This is the marginal effects of this image region when we do not mask this image region with respect to the case when we mask this image region. So the sharply value is the weighted sum of this marginal effects of a certain region. So we need to focus on the problem, how to mask a variable. So usually we replace the masked variable, the masked variable with the baseline value. We just use the baseline value to represent the masked variable. So how to learn the baseline value to represent the state, the masked state of this variable. Previously, different people have different setting to mask input variables. For example, some people may mask certain region, may replace the masked pixel with black color or the gray color. That means to set the masked unit to 0 or the mean value through all samples, or just blur the color of this pixel. And but all of these methods cannot ensure that they remove all information of the variable without generate new edges. It's because if we just simply use the black color or the gray color to replace the original pixel color, then we will bring in new dotted features to the image. The dotted feature will hurt the trustworthiness of the baseline value, the trustworthiness of the explanation. Because when we mask a variable, we can suppose the mask variable not to provide any signal to the model inference. So there's no method to represent the no signal state. There's no method to remove all information of the masked variables without generating new edges. In this way, we can summarize the objective of learning baseline value as follows. The input is a well-learned DNN and some input samples. The objective is that we want to learn the optimal baseline values that satisfy the following two requirements. First, we want to learn a certain baseline value for each dimension of the input sample, and the baseline value should be a constant. In this way, we can ensure that the sharply value still satisfy the aforementioned four properties. Second, the baseline value needs to represent the no signal state as much as possible. That means the baseline, when we replace a certain pixel with the baseline value, then this pixel is supposed not to provide any further signals, to the inference process. So in this way, we can ensure that the all signals of this pixel are masked to boost the trustworthiness of the sharply value. Before I introduce how to learn the baseline value, let's first introduce the multivariate interactions. Based on the multivariate interactions, we can decompose the overall network output, Vn, into a constant bias plus the sum of marginal benefit from interaction of all variables in S. The massive combination of input variables. Each combination of input variables can form a certain interactions. So we can decompose the overall network output to a constant sum and the utility or the benefit of all types of interactions between all input variables. This operation is very meaningful. That means we can transform a DN into an AND representation. We can decompose the overall utility of a neural network into a utility of different multivariate interactions. This is a bias. And for example, Vn means the overall output of a neural network. And the first term is a constant bias. And the following three terms are elementary interaction components. That means this is the utility of the interaction between pixels in the hand part. This is the interaction utility of the interaction between pixels in the tail part. And this is the interaction between pixels in the torso part. In this, we can simply transfer the network output into the sum of utility of the different interaction patterns. So in this way, we can classify all the interaction patterns into two types, the salient patterns and the noisy patterns. But note that there are many patterns. For example, if there are only 10 input units, then there will be 1024, a total of 1024 interaction patterns. So there are a huge number of interaction patterns. But theoretically, we can classify them into two types. One is the salient patterns, and one is the second type is the noisy patterns. Most of patterns are noisy patterns. When the IS, that's the utility of the pattern, have little influence to the prediction. That means the absolute value of IS is very small. Only very few interaction patterns has significant influence on the prediction. So when the absolute value of IS is large. So in this way, we can transfer the network representation into a symbolic representation of interaction patterns. Each interaction pattern indicates the interaction within a small set of input units, then in collaboration within a small set of input pixels. And we just count how many interactions have considerable influence to the output and how many interaction has little influence on the output. So in this way, we can use the number of salient interaction to represent the signal state of the neural network. We can learn baseline so that the learning baseline value is equivalent to the learning the baseline value that activates the least number of salient patterns. That means we want to learn the baseline value that is most likely to represent the no signal state. So to this end, we have two conclusions. First, how to learn the target of learning optimal baseline value is that we want to learn the baseline value represent the no signal state of this variable. Second, how to represent the no signal state of this variable. That means we can use the number of salient patterns to represent the overall signal state encoded in the neural network. To this end, we can learn the baseline value that minimizes the number of salient patterns. So in this way, we can use the number of salient patterns to represent the complexity of the signal state, and we can learn the baseline value to to minimize the number of the ceiling patterns, to make sure that the baseline value, actually, if we use the baseline value to replace the pixels, we can make these pixels do not produce any signal and do not affect the inference process of the neural network to repair the no signal state. In order to minimize the number of interaction patterns, let us first focus on the activation rate of each interaction. Let us first focus on the high-order interaction. High-order interaction means that the interaction consists of a large number of input variables, and in contrast, low-order interactions consist of very few input variables. Let us assume that for each input variable, the probability of this input variable being masked is a constant, for example 0.5. Then the probability of a high-order interaction be triggered is much smaller than the low-order interaction's activation rate. It's because an interaction is triggered if and only if all input units of these interactions are not masked. Otherwise, if any input variable of this interaction is masked, then this interaction will not be triggered. So in this way, we can rewrite the output of the neural network into a bias as a sum of a bias and the sum of low-order interactions and the sum of high-order interactions. You can simply consider that the sum of low-order interactions and high-order interactions is a constant. In this way, we have two conclusions. The first conclusion is that the high-order interactions usually have a low activation rate because it contains many input variables. So it more likely is less likely to be triggered. So the high-order interactions will have a sparsely activated. It's usually sparsely activated. And on the other hand, the sum of interaction, low-order interaction, and the sum of high-order interaction is a constant. So in this way, we want to reduce the signal represented by the low interaction. This is equivalent to the strengthening the signal represented by high-order interactions because the sum of low-order interaction and high-order interaction is a constant. So in this way, by reducing the signal represented by low-order interactions and strengthening the signal represented by high-order interaction, we can make most signals are sparsely activated. Then let us introduce how to reduce the low-order interaction. We prove that low-order Shapley values only contain low-order interactions. So we propose an approximate yet efficient solution that's penalizing the low-order Shapley values instead of directly penalizing the interaction. Based on this loss function, we can successfully reduce the ratio of low-order Shapley values and boost the influence of high-order Shapley values. So in this way, we can boost the influence of high-order interactions and reduce the influence of low-order interactions. We reduce the significance of low-order interactions. In this way, we can learn the baseline value that minimize the strength of low-order interaction and strength the influence of the held interaction. In this way, we can learn the baseline value that minimize the number of ceiling patterns in the neural networks. In this slide, I will discuss the connection between the multivariate interactions and other metrics. So we first connecting the interaction i's to the Shapley value. This is we can get this equation. So the Shapley value can be considered as a sum of different order interactions. And second, we can connect the interaction with the Shapley interaction index. And you can consider the used interaction. The used interaction is a special case, represent a special case of the Shapley interaction index. This slide visualizes the Shapley values computed based on the learned baseline values. First, let us see these two heat maps. These two heat maps visualize two baseline values, the map of baseline values learned based on the different parameter initializations. These baseline values are shared by all the images in the MiniStep dataset. We can find that the baseline value mainly focus on the foreground. And based on the learned baseline values, we can compute the corresponding Shapley values. And we find that the baseline value learned by our method generate less noisy Shapley values than other baseline values. This is the Shapley values computed based on other baseline values. This is the Shapley values computed based on the learned baseline values. Our Shapley value are less noisy than the other Shapley values. This slide compares the Shapley value computed based on the learned baseline values and the other Shapley values. We can find out that the Shapley value computed based on our baseline values are consistent with the Sharp method and the Sage method, but the Shapley value computed on other baseline value are conflict with each other. So this figure shows that the Shapley value computed based on our baseline values are more convincing than the Shapley value based on other baseline values. In order to verify the correctness of the learned baseline values, we need to compare the learned baseline values and the ground truth baseline values. But the problem is that on images, there are no ground truth baseline values for verification, because the ground truth of baseline values is the baseline value that that provide no signals for inference. So it's very difficult for us to construct the ground truth baseline values on most tasks, for example, for image classification and natural language processing. But anyway, we can generate functions whose ground truth of the baseline value could be easily determined. So we construct these functions. We use these functions. The baseline value of these functions can be relatively easy to determine. So BI star indicates the ground truth baseline values. Let's consider the input of xi is a binary variable. So the baseline value of this function is also binary. So we consider here for x1, x2, x3, for the product of x1, x2, x3, the baseline value of x1, x2, and x3 is 0. It's 0 because when we set x1, x2, or x3 equal to 0, this term will not be activated. So it boosts the frequency of the first term not to be activated. So we can simply determine the ground truth baseline value for this function. Then we learn the baseline value on these functions and verify the correctness of the learned baseline values. We use this metric to evaluate the accuracy of the learned baseline values. If the ground truth of this baseline value is equal to 1, then if we learned baseline value is greater than 0.5, we consider it an accurate baseline value. Otherwise, if the ground truth of this baseline value is 0, then the learned baseline value is supposed to be smaller than supposed to be less than 0.5. In this case, I evaluate the accuracy of the learned baseline values. In most cases, the accuracy is above 90%, showing that our method could effectively learn correct baseline value. Then, besides the Sharpe value, can we unify all the other attribution methods using the game theoretical interactions? This question will be answered by Dr. Huiqi Deng at the Sun Yat-sen University.
Hello everyone. In this talk, we'll show the relationship between attribution explanations and the game theoretical interactions. We demonstrate that most existing attribution methods can be unified by interactions. Firstly, we will introduce the definition of attribution. Attribution is a branch of semantic explanations. It aims to infer the contribution score or importance score of each individual feature. For this input image, it's classified as a cat, and the attribution heat map aims to answer which pixels will contribute more to the prediction. Specifically, we will get an attribution vector A, where AI is the contribution of the pixel xi to the prediction. Recently, many attribution methods are proposed. They are built upon various heuristics and different formulations. For example, the gradient times input is based on the sensitivity idea. Another example, occlusion 1 and occlusion patch are based on perturbation idea. They occlude one pixel or one patch and then observe how the prediction will change. In addition, Epsilon LRP and deep lift follows the idea of layer-wise decomposition and so on. However, there are some problems of attribution explanations. Firstly, the attribution problem is not well defined. The attribution often refers to the contribution score or importance score. However, such definition is uninformative for how to assign the contribution. Secondly, many attribution methods are based on different heuristics. This results in these methods have few theoretical foundations, no maturity, and difficult to compile theoretically. So, in this paper, we aim to address these two problems. Our main contribution have three parts. Firstly, we offer a theoretical foundation to the attribution problem. Secondly, 14 attribution methods with different formulations are unified into the proposed framework. Thirdly, we propose principles for a reasonable attribution and then assess the fairness of existing attribution methods. We will first introduce our proposed Taylor attribution framework. Attribution problem input a pre-trained model F, an input sample X to be explained, and a baseline point X tutor. It means no signal state, and the output is expected to an attribution vector. Actually, many attribution methods aims to distribute the output of X with respect to the baseline X tutor to each feature. That is to say, we want to decompose the fx minus fx tutor into the sum of AI. Note that the fx minus fx tilde corresponds to Vn minus V empty in game theory. However, there are infinite possible cases for such decomposition. Then, which one is reasonable? It's challenging to answer this question because the DNN model is too complex to analyze. So, the basic idea of our proposed Taylor attribution framework is, first, we use a high-order Taylor expansion function to approximate the fx minus fx tilde. Then the Taylor expansion function can be explicitly divided into the independent and interactive parts. Finally, the attribution can be expressed as a function of Taylor independent and interactive terms. Next, we will give a typical example, second-order Taylor attribution, to illustrate this idea. Note that second-order case can be naturally expanded to high-order cases. For example, we conduct second-order Taylor expansions, as shown in equation 1. We see that the expansion function can be explicitly divided into the first-order terms, high-order independent terms, and high-order interaction terms. We use Ti alpha, Ti gamma, and Is to denote the three type terms, respectively. Finally, because our attribution vector can be considered as a decomposition of fx minus fx tilde, then attribution can be expressed as a function of the three type terms. Our Taylor interaction terms is closely connected to Shapley-Taylor interaction index in game theory. Shapley-Taylor interaction index measures the Taylor interactions of subsets with at almost k players. We show that when k equals to the n, that is, if we consider the interactions of all subsets, then JNS equals to our IS. That is to say, our IS is a special case of Shapley-Taylor interaction index. Secondly, we prove that 14 attribution methods with different formulas can be unified into the proposed Taylor attribution framework. Specifically, their attribution maps can be expressed as a weighted sum of the three type terms. As shown the following equation, we can see that here alpha I, gamma I, and the CIS are the coefficients. The table is an overview of the unification. Next, we will introduce the unifications in details. Firstly, we'll introduce the gradient times input. Gradient times input produces the attribution maps with improved sharpness. It multiplies the gradients with the input. We show that in gradient times input can be unified into the Taylor attribution framework, and its corresponding coefficients are alpha equals to 1, gamma equals to 0, and CIS equals to 0. That is to say, gradient times input only assigns the first order terms of xi to the xi. Secondly, Epsilon LRP. Epsilon LRP produces attribution maps by distributing the output in proportional according to the input. It always proceeds in a line-wise manner. We show that in Epsilon LRP, if ReLU is used as activation function, then it can be unified into the Taylor attribution framework. In Epsilon LRP, alpha I equals to 1, gamma I equals to 0, and CIS equals to 0. That is to say, Epsilon LRP only assigns the first order terms when the ReLU activation is applied. The next one is grade CAM. GradCam computes the importance of each channel by conducting global average pooling to the gradients. Then it will perform a linear combination. We show that when we define the global average pooled feature as f, then fx, original model fx, can be considered as a function of f, hf. Then in GradCam, alpha I equals to 1, gamma I equals to 0, cis equals to 0. That is to say, GradCam assigns the first order terms of the function h instead of f. Then we'll discuss about the occlusion 1 and occlusion patch. The intuition is occlusion 1 and occlusion patch. They will occlude one pixel or one patch and then observe how the prediction changes. We show that the two methods can be unified into the Taylor framework. In occlusion 1, we have L alpha 1, alpha I equals to 1, gamma I equals to 1, and if I belongs to S, CIS equals to 1, else CIS equal to 0. That is to say, our occlusion 1 assigns the first order term, high order independent terms of xi, and all interactions involving xi to the feature xi. Next is a typical solution concept, Shapley value. Shapley value obtains the attribution map by averaging the marginal contribution of xi to a correlation S. Then it will averages all possible correlations involving xi. We show that Shapley value can be unified into the Taylor attribution framework. In Shapley value, the corresponding coefficients are alpha I equals to I, gamma I equals to I, and if I belongs to S, CIS equals to 1 over S, else CIS equals to 0. That is specifically, Shapley value will assign the first order independent terms of xi and 1 over S proportional interactions involving xi to the feature xi. Then we'll discuss about integrated gradients. It produces the attribution map by integrating the gradients along a straight line from baseline x tutor to input x. In integrated gradients, we can obtain that alpha I equals to 1, gamma I equals to 1, and if I belongs to S, and for a formulation pi equals to k1, k2 to kn, the CIS pi equals to ki over k, well k equals to k1 plus k2 to k plus kn. Else if I doesn't belong to S, CIS equals to 0. In brief, integrated gradients assigns the first order term in the independent terms of xi and ki over k proportional of interaction term xi ki, x2 k2, xn kn to xi. We give a simple example. For example, in this term, the total degrees are 4, and the degrees of x2 is 3. So the coefficients are 3 over 4. Next one is deep-lift rescale. Deep-lift rescale propagates the output difference in proportion according to the input difference. Such propagation always proceeds in a lengthwise manner. We show that if we consider the attribution of L's layer and the function at L's layer and the L layer follows such formulation, that a linear combination with an activation function, then the coefficients of deep lift are as follows. We can see that deep lift rescale will show the same coefficients as integrated gradients at each layer. Then we'll talk about deep halo. Deep halo propagates all relevancies to the features with positive weights. If we define n plus as the feature subsets with positive weights and n minus as the feature subset with negative weights, then in deep halo, for features in n plus, the coefficients are as follows. We noted the final form equation. This means the interactions among features in n minus are assigned to the features in n plus. Next is the LRP alpha beta. LRP alpha beta propagates alpha times relevancies to the features with positive weight and beta times to the features with negative weight. Similarly, in LRP, for feature in n plus, the coefficients can be expressed as follows. We can see that the coefficients are R times the coefficients in deep halo attribution. The last category is expected attribution. Expected attribution can reduce the risk that attribution is dominated by a specific baseline. The averages the attributions over multiple baselines, as shown in equation 1. Here, AI basic is the attribution obtained by the previous basic methods. It's obvious that if we combine the equation 1 with the previous reformulations, expected attributions can be unified into the Taylor attribution framework. For example, the expected gradients, expected deep lift, and deep sharply. Thirdly, and finally, we propose principles for a reasonable attribution. Then we assess the fairness of existing attribution methods. Previously, we have proved that attribution maps of 14 methods can be unified as the following form. That is, a weighted sum of the three types: first-order terms, high-order independent terms, and high-order interactions. Then, how to define a reasonable attribution? What principle should we have? We propose two principles for reasonable attribution. First, in this figure, we can see that the first-order term of xi and the high-order independent term of xi should be all assigned to xi. That is to say, alpha I equals to 1, gamma I equals to 1. In addition, all interactions of S involving xi should be assigned to xi. The interactions of not involving xi should not be assigned to xi. That is to say, if I belongs to S, CIS should be larger than 0, and if I doesn't belong to S, CIS should be 0. Another principle is interactions of alien correlations should be all distributed to the players in S instead of other players. That is to say, sigma CIS should be equal to 1. In this figure, that is to say, the W1 plus W2 weights should be equal to 1. Fine. These principles can be applied to assess the fairness of existing methods. We'll give two typical examples. For example, according to the reformulation of Shapley value, we can see that Shapley value well satisfies the two principles, and the interaction of S are evenly assigned to the players in S. For example, we see that the interactions between two players will assign 1/2 to the purple people and 1/2 to the green people. For the interactions among three players, will assign 1/3 to each player. In this sense, Shapley value is a fair attribution. Another example is occlusion 1. We see that occlusion 1 satisfies the principal 1 and doesn't satisfy principal 2. Based on their coefficients, we can see that sigma CIS equals to the number of players in S. So we can get that the interactions of F are repeatedly assigned to each player. And that's all for this.
In the previous section, I introduced how to define interaction in game theory and introduced how to determine and learn baseline value for the Shapley value. In this section, I will introduce what's the relationship between the interaction and the visual concept, how to use the game theoretical interaction to explain how a DNN encodes visual concept. In order to explain how a DNN encodes textures and shapes, let us reintroduce the multi-order interactions. The multi-order interaction measures the complexity of the interaction between two pixels. Let us consider pixels I and j here. These two pixels are pixel I and j. The interaction between two pixels I and j does not only depend on these two pixels, but also depend on the contextual pixels around these two pixels. So the order of interaction measures the number of contextual pixels involved in the interaction between I and j. If there is a large number of pixels involved in the interaction between I and j, we consider this is a high-order interaction. If just a very few pixels are involved in the interaction between I and j, we consider this is a low-order interaction. So in this way, low-order interaction mainly represent simple and common concepts, and the middle-order interactions mainly represent the middle complex context and the middle complex concepts. And the high-order interactions are the interaction consisting of a large number of pixels. So the high-order interactions mainly represent the memory of specific large-scale and complex concepts. We also derive 7 properties for multi-order interactions, including the marginal contribution property, accumulation property, efficiency property, linearity property, independency property, symmetry property, sumability property. So let us focus on another issue. What's the relationship between the interaction and the visual concept? We will explain this issue from 4 perspectives: how to understand the encoding of textures, how to understand the difference between texture and shapes, how to understand the large-scale visual concept, and how to understand the outlier concepts. The first issue is understanding the encoding of textures. We find that low-order interactions usually represent common and widely shared local textures, but the middle-order interactions usually represent more complex textures. There is a hypothesis that if we only focus on the classification of very few textures, so it's a simple classification of textures because we only classify very few textures, then the DNN usually use low-order interactions. But if we need to classify a large number of textures, or massive fine-grained textures which are similar to each other, then the algorithm will force the DNN to encode middle-order interactions. That's the middle complex interaction, which subtly distinguish the fine-grained features, the fine-grained textures. For example, here, this is a case for a simple classification of textures. For example, when we classify 11 texture categories. The texture in different categories are dramatically different from each other, so the classification is simple. In this case, the DNN encodes low-order interactions. But if we classify these two types of textures, the textures are very similar to each other. So the classification is difficult. In this case, the DNN will memorize middle-order interactions. That's the middle complex interactions to subtly distinguish such fine-grained textures. In order to verify the hypothesis that the fine-grained texture classification made the DNN encode fewer but more complex middle-order interactions, we designed this metric Fm. It measures the relative strength of the mth order interaction. To this end, we designed 3 experiments. In the first experiment, we conduct the simple classification of 11 texture categories. The second experiment is the classification of 66 texture categories. And the third experiment is the fine-grained texture classification of 231 texture categories. So we can get the conclusion that the stricter encoding of fine-grained textures usually lead to fewer middle-order interactions. Then we use interactions to understand the difference between textures and shapes. The conclusion is that encoding textures is usually more flexible than encoding shapes. Large-scale textures can be modeled as either the ensemble of massive local textures or the ensemble of very few middle-scale, middle-complex textures. In contrast, a large-scale shape is usually encoded as the ensemble of middle-complex shapes. So the flexibility of encoding shapes for a neural network is usually much less than the flexibility of encoding textures. For example, for this bicycle, the global structure of the bicycle is the ensemble of 3 middle-order interactions of these 3 lines, and each line is consists of a massive number of local shapes. So the distribution of the interaction order of when we encode shapes is relatively less flexible. The hypothesis is that if the DNN learned under different noisy conditions has a similar distribution of the interaction orders, then we consider the encoding of the concept is not flexible, otherwise it's flexible. To this end, we propose the metric delta Fm to measure the difference of the multi-order interaction strength between the DNN learned with little noise and the DNN with large noise. So in this case, a large delta F indicates the encoding of a concept is flexible. So our conclusion is that compared to encoding shapes, encoding textures usually had large delta F values. So compared with encoding shapes, a DNN encode textures with more flexibility. The second issue is understanding the large-scale visual concept. Sometimes the high-order interaction encode large-scale visual concept. Visual concept encoded as high-order interaction usually satisfy the following 2 requirements. First, the concept need to frequently appear in images, such as the sky background or the ocean background. Second, the interaction between the background and the foreground should be used for inference. For example, the interaction between the ocean and the foreground bird. In this case, either only the foreground or only the background is not discriminative enough for inference. The DNN needs to use the combination of the foreground and the background for inference. We propose a hypothesis. If a DNN memorizes a large-scale concept for inference, then this DNN is supposed to encode more high-order interactions. In order to verify this hypothesis, we construct two datasets. One dataset forces the DNN to hard memorize the entire large-scale concept for inference. For example, in the first dataset, we require the DNN to classify the entire bird hand away from the partial bird hands. But in the second dataset, we only classify whether the image contains bird hand or not. So it's not necessary for the DNN to encode the entire shape of the bird hand. We find that when we require the DNN to classify the entire bird hand away from the partial bird hand, the DNN had to memorize the large-scale concept for the entire bird hand. And in this case, the DNN encodes more high-order interactions. Finally, let us use game-threatening interactions to explain how a DNN encodes outliers. The hypothesis is that the classification of outlier mainly depends on high-order interactions. In order to verify this hypothesis, we construct synthetic outliers. We add small noises to 50 or 100 or 200 or 300 randomly chosen training samples from the tiny image dataset, and assign these noises images with random label to generate outliers. So in this case, if we train the neural network with more noisy samples with incorrect labels, the DNN will probably be learned to encode more outliers. So to this end, we propose two metrics to verify the hypothesis. The first metric is I-average, measures the average M-order interaction. A large value of the I-average indicates the M-order interaction made a more significant contribution to the classification. And the PM is the second metric. It measures the ratio of the M-order interaction have positive effects among all M-order interactions. A large PM value indicates the more M-order interaction contribute to the classification positively. That means the M-order interactions are more useful in classification. In order to verify the hypothesis, we compare the difference metrics I-average and PM between the outlier and the normal samples. We measure the metric of I-average and PM on outlier samples and normal samples, and we compute the difference delta I-average and delta PM. If delta I-average and delta PM for high-order interaction, then the classification of outlier mainly depend on high-order interactions. This is verify our hypothesis. In the experiment, for DNN trained using this set contain different number of outliers. Delta I-average and delta PM are greater than 0 for high-order interactions. The conclusion is that, compared to normal samples, the classification of the outliers mainly depend on high-order interactions. Another issue is that, can we learn meaningful features in an end-to-end manner based on interactions? This question will be answered by Dr. Wen Shen at Tongji University.
Hello, everyone. I will introduce our study about learning compositional and interpretable features. And based on this, I will discuss about the relationship between interactions and visual concepts. Convolutional neural networks have exhibited a superior performance in many visual tasks. However, feature maps of a filter in a traditional CNN are usually chaotic. For example, feature maps of filter 1 contain both the visual concepts of the bird's head and the bird's wing. This hampers the interpretability of CNNs. To improve the interpretability of CNNs, some previous studies disentangle visual concepts from chaotic feature maps and learn interpretable features. I will introduce 3 studies of learning interpretable features, including the explanatory graph, the interpretable CNN, and our compositional CNN. In an explanatory graph, each node represents a pattern of an object. A filter may encode multiple patterns. In the interpretable CNN, each filter is forced to only encode a specific pattern of an object part. In our compositional CNN, each filter is forced to represent a specific object part or image region. Compared with the explanatory graph, where each filter may encode multiple patterns, the interpretable CNN and compositional CNN have stronger interpretability, where each filter only encodes a specific pattern. Furthermore, compared with the interpretable CNN, where each filter can only represent an object part in ball-like areas, each filter in a compositional CNN can encode an object part with a specific shape or the image region without a specific structure. Therefore, the compositional CNN has stronger representation power. All these 3 studies are exploring the interactions between filters and are aimed to learn meaningful concepts from strongly interacted filters. In particular, each node of the explanatory graph is encoded as the highly interacted activations of a few filters. For example, these filters with highly interacted activations in certain area represent the head of a horse. The interpretable CNN uses regional interaction activations of a filter to represent a specific part through different objects. In the compositional CNN, a group of filters cooperate with each other to make inferences. These cooperative features have strong interactions. I will introduce these 3 studies below. First is the explanatory graph, which was published in IJCAI 2018. This study aims to build an explanatory graph to explain the semantic hierarchy hidden inside the network. In an explanatory graph, each node is encoded as the highly interacted activations of a few filters. The graph has multiple layers, corresponding to multiple convolutional layers of the CNN. Here, each node of the explanatory graph represents a pattern of an object part, for example, the horse head. A filter may encode multiple patterns, each pattern corresponding to a node. Each edge of the explanatory graph reflects the co-activation relationships and spatial relationships between 2 patterns. For example, the mixture of the head pattern and the neck pattern is disentangled from a filter's feature map. The explanatory graph can summarize complex distributions of neural activations into a few patterns. In other words, a few nodes. Each pattern consistently represents the same part among different images. For example, one node represents the mouth pattern and one node represents the head pattern. Besides, the noisy activations on background are filtered out from each feature map. Specifically, those activations that have weak interactions among different filters are filtered out. Given a pre-trained CNN trained for classification, segmentation, or other tasks, we can learn an explanatory graph. This method has wide applications, which can be applied to various architectures. To automatically learn an explanatory graph with tens of thousands of nodes, a mixture of patterns are used to fit activation distributions of a feature map, just like Gaussian mixture model. Here, a feature map of a filter corresponding to a distribution of activation entities. In the explanatory graph, each pattern is connected in a low convolutional layer to some patterns in a neighboring upper convolutional layer. Part patterns are mined layer by layer. Given patterns mined from the upper convolutional layer, activation peaks, which keep stable spatial relationships with specific upper convolutional layer patterns among different regions, are selected as part patterns in the current convolutional layer. Patterns mined in an upper convolutional layer represent large parts, while patterns mined in a low convolutional layer represent small parts. Edges encode spatial relationships between co-activated patterns of different convolutional layers. Therefore, to learn an explanatory graph, we need to learn connections between nodes and spatial relationships between connected nodes. Then, based on such connections and spatial relationships, we disentangle feature maps of convolutional layers. The upper figure shows performance of nodes in the explanatory graph. Each node represents a meaningful concept. The low figure shows performance of row filters in the CNN. Each filter may represent several meaningful concepts. Next, I will introduce the interpretable CNN, which was published in CVPR 2018. This study proposes a method to modify a traditional CNN to an interpretable CNN without additional part annotations. In the interpretable CNN, each filter represents a specific part through different objects. For example, feature maps of filter 2 represent the bird head through different birds. Given training samples xi, yi for a certain task, without annotations of parts or textures, we aim to learn an interpretable CNN with disentangled filters. To this end, we add a loss to each channel to construct an interpretable convolutional layer. The loss contains two terms, the task loss and the filter loss. The filter loss boosts the mutual information between feature maps X and a set of pre-trained templates T. A template T mu I describes the ideal distribution of activations for the feature map X when the target part mainly triggered the ith unit in X. To help understand the filter loss, we rewrite the function into three terms: a constant, the entropy of intercategory activations, and the entropy of the spatial distribution of activations. Using this filter loss, we can learn disentangled feature maps of object parts from chaotic feature maps. Here we give a toy example of the learning process. The loss encourages a low interclass entropy. In other words, the loss increases the regional activations with strong interactions. Besides, the loss encourages a low spatial entropy. Here we can see, with learning, each filter gradually represents only one specific part of a specific object. Therefore, we can see that, after learning, filter 1 only represents the pattern of bird head, filter 2 only represents the pattern of dog head, filter 3 only represents the pattern of horse torso. Each filter in the interpretable CNN consistently represents a specific meaningful concept. However, it can only represent object part in ball-like areas, which limits the interpretability. To learn a CNN with stronger interpretability power, we propose the Compositional CNN, which has been accepted in this year's IJCAI. As aforementioned, a traditional CNN has no self-reflection of its representations. In other words, its filters cannot represent visual patterns with clear meaning. Although the interpretable CNN learning filters that represent meaningful concepts, filters of the interpretable CNN can only represent object parts in ball-like areas. In comparison with the interpretable CNN, our compositional CNN can represent object parts with a more generic manner. Each filter in a compositional CNN consistently represents a specific object part or image region through different images, while different filters represent different object parts and image regions. We aim to make a CNN automatically regularizes its features into meaningful object parts and image regions without letting people supervise its semantic representations. The compositional interpretable filters should satisfy the properties of consistency and diversity. Consistency means that each filter is supposed to be consistently activated by the same object part or the same image region through different images. While the diversity means that different filters are supposed to be activated by different object parts or image regions. Given different images, we learn the interpretable compositional CNN in an end-to-end manner without any annotations of object parts or image regions for supervision. To satisfy the above two properties, we use a set of filters to jointly represent a specific object part or image region instead of using a single filter, so as to ensure the consistency. Given a pre-trained CNN, filters in a high convolutional layer are divided into several groups. A group of filters cooperate with each other to make inferences. The cooperative features have strong interactions. Besides, we use different sets of filters to represent different object parts or image regions to ensure the diversity. Features of filters in different groups have weak interactions. To learn a compositional layer, we add a specific filter loss to the intermediate layer in a CNN. The molecular of this filter loss measures the similarity between filters in the same group AK. For example, these 4 filters have similar activation regimes. In other words, these filters have strong interactions. We increase the similarity between filters in the same group to ensure the consistency. The denominator of this filter loss measures the similarity between filters in AK and all filters in the target layer. For example, the left 4 filters and the right 4 filters have different activation regimes. In other words, these filters have weak interactions. We decrease the similarity between filters in different groups to ensure the diversity. In real implementation, we propose to use a kernel function to measure the similarity between 2 filters I and J. Here rho ij denotes the Pearson's correlation coefficient between variables xii and xji through different images. Here x denotes the feature map. In this way, Sij measures the similarity between feature maps of filters I and J. Therefore, this filter loss forces filters in the same group have similar feature maps, which ensures the clarity and the stability of the visual patterns represented by each filter in this group. Meanwhile, the slight difference of these feature maps encodes fine-grained variety of the same type of object parts or image regions. Besides, the loss also makes filters in different groups have different feature maps, which ensures the diversity of the visual patterns represented by different groups of filters. This filter loss aims to simultaneously optimize parameters theta of the CNN and the partition A. We find that when we fix theta, the minimization of loss theta A is essentially equivalent to the problem of the spectral clustering. We can rewrite loss theta A as this equation. In this way, A can be optimized by applying the clustering technology. Applying the clustering technique. This filter loss can be broadly applied to different tasks, such as object classification and segmentation. We have applied our filter loss to 6 different architectures. Here we show the receptive fields corresponding to compositional filters feature maps. Each column corresponds to a certain filter. Note that we manually classify filters into part filters and region filters to help understand the visual patterns represented by the filter. In compositional CNNs given different images, each filter consistently represents the same object part or the same image region. Different filters represent different object parts or image regions. In comparison, filters in an interpretable CNN could only represent small parts in ball-like areas. Taking the human face image as an example, visual patterns encoded by our compositional CNN cover the cheeks, top of the head, eyes, forehead, eyebrows, hair, chin, and so on, while visual patterns encoded by the interpretable CNN only concentrated in the center of the face. In addition, part filters in the compositional CNN usually encode more complex shapes than those in the interpretable CNN. We also compare the performance of learning interpretable filters in different convolutional layers. We find that filters of a high convolutional layer usually represent object parts or image regions, while filters of a middle convolutional layer usually represent local textures or local shapes. We further explore the effects of different values of groups number k. The experimental results show that as group number increases, more detailed visual patterns are learned. This figure shows distributions of visual patterns that are encoded in interpretable filters of an interpretable CNN and our compositional CNN. Results indicate that interpretable filters of a compositional CNN explain much more regions in an image than those of an ICNN. We also use t-SNE to visualize filters in a compositional CNN and a traditional CNN. Results show that feature maps of a compositional CNN seem more clustered than those of a traditional CNN. To evaluate the interpretability of filters, we design a metric to measure the consistency of visual patterns represented by a filter through different images. Ideally, an interpretable filter is supposed to have high consistency. We compute the probability of a filter being associated with a ground truth semantic concept in a specific image, for example, the bird head. Then we define the inconsistency of visual patterns as the entropy of such probabilities over different semantic concepts. Besides, we evaluate the diversity of visual patterns represented by filters, which is a significant factor neglected in previous studies. In this study, the diversity of visual patterns is approximately quantified as a number of pixels, which has been explained by a CNN. We determine that a pixel is explained by a CNN if this pixel is explained by some filters. Results show that under the same diversity of visual patterns, compositional CNNs exhibit higher consistency of visual patterns than traditional CNNs and ICNNs. Besides, compositional CNNs always show higher diversity than ICNNs. Traditional CNNs show low consistency of visual patterns, which are close to that of randomly synthesized feature maps. This indicates that, in terms of filter interpretability, features of filters in traditional CNNs do not show significantly better consistency than synthesized random features. This figure shows the inconsistency diversity curves of different CNNs. The compositional CNN always shows better consistency and diversity than the interpretable CNN and the traditional CNNs. This table compares the classification accuracy between ICNNs and compositional CNNs revised from different classic CNNs. Compositional CNNs exhibit comparable classification performance with traditional CNNs. Besides, compositional CNNs achieve higher accuracy than ICNNs in most comparisons. Thank you.
In the previous section, I discussed how to define the interaction in game theory, how to determine baseline value for Shapley value. What's the relationship between interaction and the visual concept? What's the relationship between interaction and aesthetic appreciation? In this section, I will talk about the relationship between the interaction and the generalization power of the neural network. In short, we have three conclusions. First, theoretically, we prove that the dropout operation can decrease the strength of interaction modeled by DNN. Second, there is a negative correlation between the strength of interaction and the generalization power of the neural network. Third, the generalization ability of neural network can be enhanced by directly controlling the strength of interaction. This figure shows that the dropout can decrease the strength of interaction modeled by the DNN. And this table shows that there is a negative relationship between the interaction and the generalization power of the neural network. The more overfitting of the neural network usually lead to the more interactions between the input units. In this way, we can simply boost the generalization power of the neural network by directly suppressing the interaction modeled by the neural network. Based on the interaction, we can improve the utility of dropout. For example, there are two advantages. First, our loss function can explicitly control the DN between the overfitting and underfitting. By control the weight lambda, we can explicitly push the DN from overfitting to underfitting. Second, we can solve the issue that the dropout is not compatible with the batch normalization. Our loss function is compatible with the batch normalization operation. This is the result of our loss function. By set different parameter lambda, we can explicitly control the model to any point between the overfitting and the underfitting. In the previous section, I introduced how to define the interaction in game theory, how to determine the baseline value for a Shapley value, and what's the relationship between the interaction and the encoding of visual concept, and how to use the theoretical game theoretical interaction to explain the aesthetic appreciation, and how to use the game theoretical interaction to explain the generalization power of the neural network. In this section, I will introduce the relationship between the interaction and the adversarial transferability. This study is motivated by the following phenomenon, that the multi-step tags usually suffer more from overfitting problem than the single-step tags. It means that the multi-step tags usually has much lower adversarial transferability than the single-step tags. On the other hand, the interaction of the perturbation units in the multi-step attacks are much stronger than the interaction between perturbation units in the single-step attacks. We conducted experiment to show that there is a very clear negative correlation between the strength of interaction and the adversarial transferability. In this way, we propose a hypothesis that we can reduce the interaction of perturbation units in the adversarial sample in order to boost the transferability of the adversarial sample. In order to verify this hypothesis, we just find out 5 existing transferability boosting methods, and we hope to prove that this transferability boosting method can be approximately explained as the reduction of interactions. For the first 3 transferability boosting methods, we can theoretically prove that these 3 methods reduce the interaction strength. The first method uses the momentum to boost the transferability of the adversarial sample. The second method uses smooth gradient to generate adversarial samples with higher transferability. We prove it in theory that all the 3 methods can be explained as the reduction of interactions. And we can prove all the 5 methods, the utility of all the 5 methods as that all the 5 methods reduce the interaction between the adversarial perturbation. In this way, we can summarize the common mechanism of the existing transferability boosting methods, and we can use this common mechanism to further boost the performance of such methods. We can combine existing methods with the interaction reduction loss, and to further boost the performance of existing methods. Okay, in previous section, I introduced the definition of interactions and how to use the interaction to determine baseline value of the Shapley value, and they discussed the relationship between the game theoretical interaction with visual concept, the relationship between the game theoretical interaction with the aesthetical appreciation, the generalization point, and the adversarial transferability. In the final section, I will discuss the relationship between the interaction and the adversarial robustness. This slide summarizes the previous explanation of the adversarial robustness. Some studies explain adversarial samples as due to the nonlinearity of the feature representation, and adversarial samples explain the adversarial perturbations as the non-robust but discriminative features. Some people explain the adversarial training as the learning of general shape of object, or the enumeration of all possible adversarial samples. And in terms of explaining adversarial robustness, many people prove the theoretical bound of the adversarial robustness instead of provide a heuristic understanding of why a model is adversarially robust or not. In this way, the contribution of this paper can be summarized as follows. First, we discover that the adversarial attacks mainly affect high-order interaction between input variables. Second, the adversarial training can be explained as the learning of the more discriminative and low-order interactions, which explains the utility of the adversarial training, and explain the reason why adversarial training can boost the robustness of the DNN. Third, we propose a unified explanation for several adversarial defense methods. First, let's focus on the first part. We discover that adversarial attacks mainly affect high-order interactions between input variables. Adversarial attacks mainly affect high-order interaction. To this end, given a normal sample x, let x tilde equal to x plus adversarial perturbation. Then we can decompose the total adversarial utility of the perturbation into the attacking utility on different interactions of different orders. We discover that adversarial attacks mainly affect the high-order interaction between two input variables, and low-order interactions are usually robust to adversarial attacks. Then we discover that the adversarial training boosts the robustness of DNNs by learning more discriminative low-order interactions. We find that in the adversarially trained DNN, attacking utility of a high-order interaction significantly decreased. Furthermore, we discover that in the adversarially learned DNN, the low-order interactions are much more disentangled than the normally trained DNN. It means that in the adversarially trained DNN, the low-order interactions are more category-specific and more discriminating. It means that the learning of more discriminative and more category-specific low-order interaction can strengthen the robustness of high-order interactions. Finally, we propose a unified explanation of several adversarial defense methods. This slide focuses on 4 adversarial defense methods. The first 2 methods were proposed to detect adversarial samples. These 2 methods can be explained as the detection of the highest order interaction. The last 2 methods are methods of boosting the robustness of the model. These 2 methods can be explained as removing sensitive high-order interactions in order to boost the adversarial robustness. Thank you very much.